Alright, we're finding the exact area under this curve on this interval, and we're asked to use the limit of a Riemann sum. We're going to assume a right-hand approach. For starters, we want to figure out what delta x is. To find delta x, we take the end of our interval value and subtract the beginning interval value. So 3 minus negative 2 would be the same as 3 plus 2, that'd be 5. We take that and divide by n. Now I've got my setup here that I have to remember for my limit of a Riemann sum. As I start to plug in some values to this setup, I understand the limit notation stays and the sigma notation stays for quite a few steps on this problem, because initially this problem's all about doing algebra. So plugging in now to my function, I plug in what a is. A is where the interval begins, that's negative 2. Plus I times delta x. Delta x we found to be 5 over n, so it's 5 over n I. So I've got this delta x, but now I've got to remember to multiply on this delta x. Well, delta x is still 5 over n. At this stage, it'd be useful to figure out what the function is going to look like if I take negative 2 plus 5 over ni and I substitute back into the function for x. So I've got my limit still, got my sigma notation still. And now substituting in for x, negative 2 plus 5 over ni. Since I'm substituting that in for x, we're squaring that. And the rest of the function reads that we're adding on 5, so I make sure to add 5 down here. All of that represents my function. I'm multiplying by the delta x still, which is 5 over n. At this stage, I should expand the binomial and work on simplifying everything inside the brackets here. If I expand that binomial, I understand that means negative 2 plus 5 over ni times negative 2 plus 5 over ni. If I FOIL that out, keeping in mind I still have my limit notation, still have my sigma notation. And let's see, when I FOIL all this out, first terms would be 4 when I multiply. Now, knowing I need to add on a 5 as I collect like terms, I'm going to make this 9. As far as the outside terms and the inside terms are concerned, those are going to be the same thing. When I multiply negative 2 to 5 over ni, I get negative 10 over ni. So, two of those would be negative 20 over ni. And finally, I'm multiplying my last terms here. 5 over ni times 5 over ni. I'm going to get plus 25 over n squared I squared. All right, so I've cleaned up everything inside the brackets. Still need to multiply by this 5 over n at the end. As I multiply by that 5 over n at the end, I'm distributing it back through to these three terms. So let me carry this over to the next slide. Alright, so now I've carried everything over based on that distribution, and since I've finally simplified all this, I can use my sigma notation and apply that to each individual term as I start to use some of those I theorems that we've talked about. So the limit notation I'm not quite ready for yet, but sigma notation is dropping out because I know if I apply this sigma notation, 45 over n represents a constant, so that will get multiplied by n. The minus 100 over n squared I, well, that I, its theorem is n squared plus n over 2. I insert that in the place of I. In a similar fashion, on the last term here, the 125 over n cubed I squared, in the place of I squared, I'm going to replace that with 2n cubed plus 3n squared plus n, try to squeeze it all in here, over 6. All right, now I'm almost finished. almost ready for my final calculation. Since I'm ready for the final calculation, essentially I'm dropping the limit out, because for this first term, as I multiply things here, the ends are canceling each other, leaving me with 45. I'm subtracting for this next set here. Well, all I really need to remember to do here, because of how the canceling out works, especially as the limit's applied, all I have to remember to do here is take this 100, divide by that 2. So 100 divided by 2, get 50. And plus, for this last one, again, because of all the canceling that's involved, really all I have to remember to do is take this 125 here, multiply to that 2, and divide by this 6. Now if I do that, I get 250 over 6 in an unreduced form. But now if I go ahead and add everything up and maybe round off to 3 decimal places, I get my final answer for the exact area here using the limit of a Riemann sum. Alright, so now if we turn our attention to this problem, we have the setup here for a Riemann sum that's being used to calculate the area of a region. We're asked to express this limit as a definite integral. How we want to go about approaching this problem is kind of look at the key players we use when we're trying to evaluate a limit of a Riemann sum. You know, there's key players like a delta x. You know, what does a delta x usually look like? Well, it usually looks like some number over n. As I look at my setup here for the limit of the Riemann sum, I see a couple of expressions here where I've got some number over n, and that number happens to be a 5, so I could assume that delta x must be 5 over n. Now, other key players we think about when we set up a limit of a Riemann sum is there's usually an expression, an a plus I delta x, that we're plugging in the place of x for our original function. We're plugging into the original function. Now, if I look at this kind of pattern, based on my setup that's given here on this problem, I see my delta x here is 5 over n, so there's a 5 over n here, a 5 over n here. My attention is really focused on this part because of this I, right? It's I times delta x, so it's I times 5 over n in this case. So what that means is I add on this -1, this -1 must be my a value, so that's going to be where the interval begins for this definite integral. So if I'm looking for a definite integral that I can use to express the exact area here that I would be finding using this limit of a Riemann sum, well, I know that the interval is going to begin because of my a value at -1. And if I take this value on top of my n here for my delta x, I can just add that on to the -1, giving me 4. That's going to be where the interval ends. You think about it. Usually we take this value, subtract this value to get the value of 5 on top over n for our delta x. Okay, finally I need a function to work with here, and we'll do this with respect to x. Since I know my a plus I delta x is usually what I plug back into the function in the place of x, and I've identified that expression right here, this must represent my x, and that x is being squared. So I have x squared. I want to account for this plus 3 as well. X squared plus 3 must be the original function I'm plugging into. So this would be my definite integral.